Gain the latest news from our experts in the field straight to your hands. Sign up for our weekly tech service where we provide quick and to-the-point videos, shot on site to help you plan your planting day, know when to scout and which diseases are present in your area, become aware of upcoming tech and new seed options, precisely time fungicide, insecticide, and chemical application for best financial returns, and much more. Every choice you make as a farmer matters on the field. With more information on hand, the better agronomic decisions you can make, keeping your ROI high, yield strong, and soil healthy for the long haul. Sign up is free and easy. Simply text the word JOIN to 844-843-9247. Cancel anytime by texting the word STOP. It's just that easy. No spam, just helpful information shared once a week. Stay in the know with Liqui-Grow.
Altover family's owned and been in business for 3 generations. The West Branch location was started in 2013, finished in the fall of 2014. So it's been here for 8 years. The West Branch location is unique because we offer a full line to where we offer parts and service, small utility tractors in the Massey brand, clear up to 550 horse tractors made by Fendt. We offer Claas combines along with the Fendt combines, and then we offer full line tillage equipment and planting equipment. Altovers is a great place to work because we still live by the motto that started the business, and that is tell it like it is. The Altover family is still very engaged with the company. They're still hands-on and they always put the customer first.
Hi, my name is Jake Vossenkemper, Director of Agronomy and Research here at Liqui-Grow. Today we're on site at the West Branch Altover location, beautiful facility. We have a beautiful brand new Fendt Rogator behind us. Looking forward to seeing those things in the field. Today we have an awesome presentation coming up by Justin Glisan. He's the state climatologist. Justin is going to go over kind of the historical aspects of this about 3-year running drought we've been in, what kind of effects that's had, what the soil moisture levels are like, and then give us some predictions about what we might expect for the weather in the future and for this coming growing season. So really looking forward to that. If you have questions about the things that I cover or Justin covers, you can always ask those questions in the live chat, as well as you can email those questions to us. And if I can't directly answer your question, we can get those questions to Justin and we'll get your questions answered. And I will be back after Justin's done to talk about what are some of the agronomic implications of his current and future weather outlooks. So enjoy the presentation. We'll see you in a bit.
Good morning, everyone. My name is Justin Glisan, and I am the State Climatologist of Iowa at the Iowa Department of Agriculture and Land Stewardship. My position is a unique role across the state. We have 49 state climatologists in the United States. I'm only one of 2 that is attached to a Department of Agriculture, the other being Arkansas. So given that our state is driven by agriculture, it was very important for the state climatologist to be attached to the Department of Agriculture. And my position, in fact, is written in Iowa code. So our farmers and our legislature knew how important weather and climate is to our state, and hence why my role is a very unique role for the state. So today what I'll be discussing is what's the weather, a few different things, the 2022 climatological summary. We'll also look at various things in our current conditions, such as drought considerations, also moisture variables and snowpack, which will be vital for the next growing season. Also looking at large-scale atmospheric weather patterns across the state. These will be impactful as we move through winter into spring. And we're also seeing in the climate modeling the suggestion of a large-scale shift from La Nina to what's called ENSO neutral. And we'll get into that as we move through the presentation. And then finally, we'll look at seasonal predictability and the climatological outlooks that we get from the climate modeling. So on this current slide 3, we're looking at the 2022 final climatological summary for the state. Now, when we talk about climatology, we talk about the last full 3 decades, or the last 30 years, that we use as an averaging period. This gives us a good baseline for ranking events, whether it's a severe weather outbreak, a derecho, a blizzard, or the basic temperature and precipitation behavior across the state. So if we look at our statewide average temperature for 2022, we came in at 47.5 degrees, and that's slightly less than a degree below normal. And that ranks out of 150 years as the 47th coldest year on record. Now, on the precipitation side, we're in the 3rd year of the current drought, and we averaged about 27.25 inch of precipitation. Now, as a reminder, precipitation is anything made of water meteorologically forced out of the atmosphere. So snow, sleet, freezing rain, the liquid equivalent of the frozen hydrometeors that come out of the atmosphere, and then we get the liquid equivalent. So that was about 8.75 inches below average. And again, out of 150 years, this ranks as the 25th driest year on record. So extremely dry conditions, especially in northeastern Iowa, but definitely dryness across the state. And if we look at these rankings compared to the last colder and drier year, 2019 was a colder year, while 2012 was a drier year and the 19th driest year on record, which makes sense given that 2022 versus 2012, both drought years across the upper Midwest. This is the average temperature departure on the left and the precipitation departure on the right. On the temperature side, you'll notice green across northern Iowa. Those green colors are basically 1 to 2 degrees below average. The rest of the state, we see that gray color, so near normal for what we would expect. On the temperature side, when we look at temperature variability through the months, we do see warm months, we do see cold months, but overall, annually, we basically are near average, +1, -1 degree. In those more extreme years, drought years or flood years, we do see colder or warmer extremes. But where we do see more variability, and definitely more variability through the last 30 years, is on the precipitation side. So wherever you see those warmer colors on the map on the right-hand side, that's where we've seen precipitation deficits really stack up. So those warmer colors that we see, anywhere from 12 to 15 inches below average in western Iowa, and then a little pocket in southeastern Iowa. And those are where we see the drought core, the structural drought that I'll discuss a little later. Now, if we look at the breakdown of the months from January through December of 2022, we have a departure from normal in degrees Fahrenheit, which is the vertical axis. So if we look at the blue bars, those are months in which we were colder than average. And on the flip side, those red bars are warmer than average months. You notice that through the growing season, May, June through September, we had warmer than average temperatures. And this coincided with a drier signal in the precipitation. We do see in January, February, April, and December below average temperatures, anywhere from 3 to 5 degrees below average. Those were basically balanced out by the warmer temperatures during the growing season, but definitely colder months than we did see warmer months. If we look at the precipitation behavior, this is a stark reminder on drought conditions across the state, but also how dry the growing season was. Only 3 months in 2022 saw above average precipitation, and 2 of those months at the end of the year, November and December. March, we also saw slightly above average, near 3/4 inch above average precipitation. But then April through October, we definitely saw very dry conditions across much of the state. Now, luckily, we had timely rainfalls that held the crop on. We were slightly below the record yields that we saw last year in the second year of drought. But overall, when we do see these precipitation deficits through the growing season, through the wettest part of the year climatologically, that's where we really see precipitation deficits stack up. And going back 3 years in the driest part of the state, northwestern Iowa, we have precipitation deficits on the order of 15 to 25 inches. And that's where we see that D3 and D4 core right now. Now, if we look at slide 7, this is the Climate Division precipitation departures. Each state across the United States is broken up into climate divisions. And these climate divisions, we have 9 across the state of Iowa. Climate Division 1 is northwestern Iowa. Climate Division 5 is central Iowa, and Climate Division 9 is southeastern Iowa, just to give you an orientation. On this map, wherever you see brown coloring is where we've seen below average precipitation. So we have a notch of below average precipitation across Iowa, Nebraska, Kansas, and then getting into the southern states, Texas and Oklahoma. Where you see those green colors is where we're above average precipitation-wise. So you look at the mid-Atlantic states, getting into Missouri, in the eastern part of the Corn Belt, wetter conditions. These wetter conditions are tied in with a more active tropical season. So more hurricanes, more tropical systems making landfall through the Gulf of Mexico and then transversing up through the mid-Atlantic states. Hence, you see more rainfall with those tropical systems, which are tied into the La Nina signal, blocks off the moisture gate into the upper Midwest, and hence you see drier conditions in Iowa. Now, we did see a bifurcation or a split in the jet stream, and that's where you see wetter conditions across North Dakota, northern parts of Minnesota, and even into Wisconsin and parts of the upper peninsula of Michigan. So a split in the jet stream, a split in the storm track gives us this particular behavior across the state. Overall, if we look at the climate divisions across the state, anywhere from 6 to 10 inches of below average precipitation. So again, a third year of drought, a third year of precipitation deficits across the state. So switching gears now, we'll look at current conditions across the state and impacts on drought, and also what we're looking at hydrologically if we look at stream flows, but also the snowpack that we see across the upper Midwest and those implications on stream flows, but also Missouri and Mississippi River levels. So on slide 9 here, we see the last 180 days or the last 6 months of precipitation across the upper Midwest, Iowa being right in the middle of the map. Wherever you see warm colors here, we've had precipitation deficits. So on the order of 2 to 4 inches across the state over 6 months, definitely in those 2 drought regions that we'll show on the drought map in the next few slides. Southeastern Iowa, but also a core in west central to northwestern Iowa. Across the rest of the state, we have those gray colors near average, so slightly below or slightly above average, but basically near where we should be over the last 6 months. If we look at the drought depiction, on the right-hand side is the current drought depiction that's released every Thursday morning versus the drought depiction from 1 year ago on this calendar date. We still had structural drought across eastern into north central Iowa, and also a core of D1 in northwestern Iowa, centered on Sioux City, but in parts further east. It's a stark reminder of the 8th wettest October in 2021 that really helped extinguish longer-term precipitation deficits in western Iowa. But as we moved through the early parts of 2022, we did see drier conditions form that exacerbated precipitation deficits going back to May and June of 2020. And that's what we talk about structural drought, that D1 to D2 corridor, where if we do get into a dry pattern, that's where we see the seeds of drought start to enhance and degradation accumulates, and we see drought expand. We see on the right-hand map here a D3 and a D4 corridor, basically 9% of the state, with D4 surrounding Sioux City. Extremely dry conditions. If we looked on a percentile basis for 100 years of weather records for a given location in that D4 region, we wouldn't expect D4 drought once but every 50 to 100 years. So we look at Sioux City for 2022 with a period of record going back to 1893. the third driest year for Sioux City on record. And that's where we see that D4 corridor, which stretches into Nebraska. Secondarily, we look in southeastern Iowa, another core of longer term precipitation deficits going back 8 to 12 months, even 16 months, where we have D2 and D3 covering counties in southeastern Iowa. So we look at the center part of the state from south central Iowa up through eastern Iowa. We have seen improvement. Recent rains in early December and snowpack in January prior to soil profiles freezing has allowed some infiltration of soil moisture, and we've seen some improvement. Now, if we were to look at a 52-week or one-year class change map of drought, wherever we see warmer colors here is where we've seen degradation in drought conditions. 1 category, 2 categories, all the way up to 4 categories in eastern or in western Iowa. So drought conditions have intensified and expanded across the state. Again, given that it was the 25th driest year on record. You look at western Iowa and northern Iowa, those climate divisions 1, 2, and 3, and then 4 in west central Iowa, top 10 driest summers, and then getting into fall, top 25 driest falls. So we really saw an enhancement of those precipitation deficits. Now, the saving grace has been temperatures haven't been anomalously warm as we've seen in the last widespread pervasive drought from 2011 to 2013. So those warmer temperatures during that time period exacerbated drier conditions. So we saw a rapid expansion of D3 and D4 drought. In this go around from 2020 through the present day, we again haven't seen anomalously warm temperatures for a long stretch. Now, of course, we've had heat waves, but we haven't seen an exacerbation of atmospheric demand for surface water vapor, and hence we have seen a slower expansion of drought across the state in western Iowa particularly. Now on slide 11 here, we'll look at the accumulation, the water year accumulation of precipitation. The water year starts in October, generally after vegetative demand, after harvest has started or hopefully completed by the end of October into November. But we look at this time period as an accumulation of precipitation for the next growing season as we start to improve or at least infiltrate more water in the soil moisture profiles. So if we look at the overlay on the bars going from left to right, October through September, we see an accumulation through the year of the expected precipitation, generally about 35 inches as a statewide average as we get into September. What I've done is I've overlaid the last 3 years, 2020 through 2022. And what you can see is as we move through the year, the water year, those dots start to intercede, they start to drop down into those bars, and that is a reflection of precipitation deficits starting to stack up. So we start off generally good in October, November, and December as we get into the driest part of the year, which is December, January, February. But then as we get into the growing season, we start to see those precipitation deficits stack up with lack of thunderstorms. On the good side of that, lack of thunderstorms, lack of severe weather. But with the lack of thunderstorms, we start to see less rainfall, and then rainfall departures really start to enhance, and that's where we see drought conditions expand. Now, if we look at the last 3 years, and the plots that I'll show you on slide 12 are the precipitation departures from the beginning of the drought in 2020. So we look at this map, and this will orient you for the next 2 maps. Wherever you see warmer colors are precipitation deficits. When we get into those red colors in west central Iowa, 12 to 16 inches of below average precipitation through 2020. That's where we saw the seeds of drought form in west central Iowa. Very dry conditions as the seeds of drought, and then we see an expansion in western Iowa. Now, on the flip side of the state, in eastern Iowa, we saw wetter conditions, anywhere from 4 to 6 inches in certain pockets of the state but generally wetter conditions in northeastern Iowa. Then we transition into 2021. We really see precipitation deficits across much of the state, save the four corners we have in northwestern, southeastern, southwestern, and northeastern Iowa. Those colder colors, that's where we've had above average precipitation through 2021. But again, you look at the drought map through 2021, D1 and D2 conditions across central, north central, and into northwestern Iowa. As a reminder, you have to take these maps 1 year at a time, but we're also stacking up precipitations through the years. So if we get into 2022, we really see very dry conditions in those two core drought regions in northwestern Iowa and southeastern Iowa, with anywhere from 12 to 16 inches of below average precipitation. Only Winneshiek and Allamakee counties in northeastern Iowa saw above average precipitation and broad-based dryness across the state. On slide 13, we look at the seasonal drought outlook, and this was issued in the middle of January, and it goes through April 30th. To orient you on this map, wherever you see brown colors are where we expect drought to persist. So generally northwestern Iowa into western Iowa, and then across the Missouri River Basin. And again, that little pocket of southeastern Iowa as well. But we do see drought removal in the eastern part of the Corn Belt, and also in eastern Iowa, where we do see D0 and D1 conditions. But overall, given those long-term precipitation deficits, we do expect drought to persist unless we get into a very active storm track. And I'll get into that when we talk about large-scale weather patterns. Again, to remind you of the ebb and flow of drought across the state, this is a time series going back into 2020. Vertical axis shows you the percent coverage of the state. The color gives you the drought category, D0 to D4. And then the horizontal axis gives you the time period. So we've seen basically 3 cycles of drought where we've had anywhere from D0 to D3 across the state. Not until 2021 did we see D4 drought start to form in western Iowa, and then a core of about 1% of D4 around Sioux City. So again, we have had improvement across the state with a more active storm track, especially in October of 2021, again, when we had the 8th wettest October in 150 years, supplying western Iowa with anywhere from a month to 2 months worth of precipitation at given locations. So we, in fact, saw drought removal in western Iowa. A key reminder, though, is with those longer-term precipitation deficits going back to 2020, when you do get into a dry stretch, those longer-term precipitation deficits are exacerbated, and hence you see drought expansion and drought degradation. Now, a function of drought, meteorologically, we expect precipitation. Drought is a lack of precipitation, a lack of moisture. We can also look at the surface and below surface to give us an indication on how dry things are. Now, if we were looking as we moved into early June of 2020, this is a soil moisture remote sense tool from a NASA Sport satellite that gives us an idea of the 0 to 80-inch soil profile. So wherever you see warmer colors here, the 20th to below percentile. So if you use a sponge as a proxy, the 100th percentile would be a soaked sponge. On the reverse side of that, where you see the 20th or below percentile, that's where we see 80% or more capacity for soil moisture in that profile. So dry conditions as we get into the wettest month of the year for the northern 2/3 of the state. If we look at the current soil moisture profile as remote sensed, going down 80 inches, very dry conditions across much of the state. We see pockets of the 5th to 2nd percentile. And again, using that sponge as a proxy, anywhere from 95 to 98% capacity for more soil moisture infiltration. Now, why this is important is we need soil moisture for the next growing season, especially if we stay in a dry pattern. The models aren't suggesting we stick in a dry pattern, and I'll get into those when we hit the outlooks, but definitely below average soil moisture as we move into the middle part of wintertime. The caveat here is the soil moisture profile is frozen, so we are not getting any infiltration. But I did mention in early December, we had widespread rainfall events that allowed for moisture to be ingested into the profile. When we do have wetter soils, we don't get a deep frost level. Now, of course, the soil is going to freeze, but drier soils will freeze faster and freeze deeper. And this has implications on moisture recovery as we get into spring. So if we look at a 6-month difference in the column relative soil moisture as a percentage, we have seen improvement anywhere from 8 to 20% improvement across southern Iowa, and even in western Iowa, 4 to 8% improvement in the driest parts of the state. Where we have seen a degradation in soil moisture has been in central and through northeastern Iowa. Now, again, another caveat there is northeastern Iowa has been a wetter part of the state. So this can be deceiving in that we are seeing wetter profiles in northeastern Iowa, but with drier conditions through fall, we have seen some degradation in the soil profiles in northeastern Iowa. But overall, we have seen good improvement, but we do need a lot more improvement. Again, I'll draw your eyes to the mid-Atlantic states along the Gulf Coast. Lots of improvement in soil moisture. And again, this is a function of a more active tropical season with Gulf landfalls. Now, if we look at another proxy for moisture, these are 28-day stream flows across the state. Wherever you see green, that's where we see normal stream flows. So if we look at inputs into our stream system across the state, this is where we see what we should see for this time of year. Now, wherever you see white on the map is where we've had river gauges freeze up, so we're not getting any readings. We do have 2 or 3 basins across the state where you see orange or red colors in which we're below or much below average. And when you're below average, you're not seeing the amount of throughput in terms of moisture. This also goes hand in hand with soil moisture. If you have dry profiles, any type of precipitation event that you get, unless it's a very, very heavy event, will soak into the soil profiles as opposed to running off into the stream system. And this is where you see below average flows in central Iowa and then in 2 basins in southern Iowa. When we talk about the soil moisture profiles, we also want to talk about soil temperatures. And this is a 4-inch soil map on slide 19 that shows what the temperature is across the state of Iowa of the 4-inch depth. Now, when you see temperatures above 32, you're seeing the possibility of snowmelt and at least shallow infiltration of moisture into the soil profile. This is important because when we do get into colder times with Arctic outbreaks of colder air, the top layer will freeze. But when you get into thaw and refreeze cycles, you're actually producing melt and refreeze events that actually exercises that soil profile. So you're getting more porosity in that shallow layer, so for deeper infiltration to occur. Now, of course, this will be important as we move into spring thaw to give us an idea of how much of that snowpack that's currently on the ground will actually get into the soil system. If we look at total frost depths across the state, we're running about 8 to 10 inches at our monitoring stations. So this gives us an idea of how deep the frost level is. Now, for drier soils with the Arctic outbreak that we saw prior to Christmas in 2022, you can see frost depths getting down to 24 inches. Luckily, with those December rainfall events, we were able again to infiltrate moisture into the profile, and that mitigated how deep the frost level got. So that at least is good news as we move into late winter and early spring. Now, if we look at snowpack across the upper Midwest, which is important for Missouri and Mississippi River levels, we do see a good snowpack from the northern half of Iowa up through the Dakotas, Minnesota, and Wisconsin. Now, this is depth of that snowpack. You'll, of course, get compaction with sunlight melting some of that snow, but you'll also get a crust that forms, and it allows that snowpack to remain through warmer periods of wintertime. But overall, if we look across the state, 4 to 8 inches south to north with higher snowpack along the Minnesota-Iowa border. Now, we often get asked, well, we have a good snowpack on the ground, but how much moisture do we actually get out of that snowpack? Well, if we look at the snow water equivalent of that snowpack, you see across the Minnesota-Iowa border, generally 2 to 4 inches of available water if that snowpack were to melt all at once. Higher amounts further north. But again, the rule of thumb that we have across the Midwest, generally 12 inches of snowfall yields about 1 inch of water. So you're not getting a good amount of water out of a very high snowpack, but any moisture helps when we do get into drought considerations. We also look at the snow depth compared to the 30-year climatology, or what we expect for this time of year. So if we look at this map on slide 21, anywhere where you see blue colors is where we have above average snowpack. Eastern Iowa, we're currently in a snow drought, another type of drought in which we're below average on snowpack. But the recent events that we've had across the state in mid-January have improved our snowpack across the state. And we see anywhere from 4 to 8 inches of above average snowpack in Western Iowa and even into Northwestern Iowa, again, the driest part of the state. Okay, on slide 23, we'll discuss what an atmospheric oscillation is. So again, this is just a fancy term for a semi-periodic behavior in the large-scale atmosphere that impacts shorter-term weather patterns across the United States. We call these teleconnections because these are patterns that are happening thousands of miles away in the Pacific that have a large-scale linkage on weather patterns over the United States, and hence where the storm track sets up. As we look at atmospheric oscillations, these patterns are what we call El Nino or La Nina for a well-known atmospheric oscillation. If we look at dominant oscillations that impact North American weather, we have various periodicities in terms of timescales, but also spatial scales. The dominant current oscillation that we see affecting the Pacific and North American weather is what we call ENSO, the El Nino Southern Oscillation. ENSO works on a multi-decadal scale. So we think of the Southern Oscillation as a large-scale weather pattern across the Pacific that works on a scale of 10 to 20 years. So you think of ENSO as a very large wheel. Then we look at El Nino and La Nina, the warm and cold phase that work on a 2 to 7 year cycle. So if we think of a large wheel as ENSO, the El Nino and La Nina phases work as a smaller wheel that oscillates within that larger wheel. So that's where we see a 2 to 7 year cycle in El Nino and La Nina phases. We also have what's called the Madden-Julian oscillation, which is a weather pattern that works on a scale of weeks to months. In weeks to months, we have 8 phases of thunderstorm activity across the Pacific that also impacts where the jet stream sets up over the United States. Where that jet stream sets up gives us an idea of where cold air versus warm air can occur, but also various precipitation events. Then we have the Arctic oscillation, which works on a time scale of weeks. When we know the phase, negative or positive, of the Arctic oscillation, it gives us an idea of impending cold air outbreaks, as we saw prior to Christmas. Then we have the North American oscillation and the Pacific decadal oscillation. I mentioned climatology, the 30-year time period that we use for averaging. We use that 30 years because we have oscillations working on different periods. That gives us a good averaging period to get a few of these cycles in. Then we get a better idea of the potential for seasonal predictability. So if we look at the El Nino Southern Oscillation, it generally tells us where thunderstorms set up over the Pacific. Now, if we look at that La Nina phase where we're currently in, we have upwelling cold Pacific waters along the tropical equator in the Pacific Ocean. That impacts the atmosphere. The atmosphere senses this colder air or colder sea surface temperature, and it produces a downward motion. Now, given that meteorology is a study of equilibrium, whenever you have a downward motion in the large scale atmosphere, at some point in the atmosphere, you have to have upward motion. And that's where we see a shift in thunderstorm behavior further west in the Pacific Basin, and that impacts where the jet stream sets up. So on slide 26 shows us the monitoring sections of the tropical Pacific that we look at for those cold or warm anomalies. And we concentrate on that Nino 3.4 region to give us an idea of how warm and cold the sea surface temperature is. In the La Nina winter interface, we have cold waters upwelling in the tropical Pacific, and that necessitates a downward motion in the atmosphere. On the right-hand side, we see this high pressure block set up, and that puts a northward dent in the polar jet stream. When you have a northward behavior in the polar jet, that blocks off colder air from the southern part of the United States, but it also allows for wetter conditions in the Pacific Northwest and the Ohio Valley and the Great Lakes. As you'll see on that plot on the right, Iowa is right in the middle of those two interfaces. So it really does depend on the strength of that La Nina to where that jet stream sets up. Another dominant oscillation that we see in the wintertime is the Arctic oscillation. This is a pressure difference between the mid and high latitudes. And whenever we see a dip in that Arctic oscillation index towards the negative side, that's where we see cold air outbreaks across the mid-latitudes across the United States. And that's the plot that we see on the far right here. Negative Arctic oscillation gives us a breakdown in the polar vortex, and we see a southward shift of very cold Arctic air, and that's where we get into Arctic air outbreaks as we saw prior to Christmas in 2022. Now, we're actually able to forecast the phase of the Arctic oscillation. So the top plot here is the actual observed pressure difference. So wherever you see the bars below the line, that's where we get into a negative phase. And the farther down the bar is, the more negative that phase is. Well, an interesting thing occurred just after the start of December, and that we started to see the forecast for the Arctic oscillation nosedive south or become more negative. So we were given about a 2-week forecast of an Arctic air outbreak around Christmas, and we saw that. So these are the things that we can build into the climate models that give us a better idea of seasonal predictability, but also short-term predictability on the scale of weeks out to a month. So on the main points for these oscillations that we see in the Pacific, on slide 31, we see these variations over various time periods, long, multi-decadal out to short, weekly, as we see in the Arctic oscillation. And these weather patterns impact the smaller scale weather patterns across the United States. So if we know the mode or the phase of an oscillation, we know we're in La Nina, we know we're in the negative phase of the Arctic oscillation, we're able to look at analog years in which we've seen this behavior, but we're also able to parameterize the climate models to behave in that way. And this gives us a better idea, again, out seasonally, of the implications on precipitation and temperature behavior. Now, there are some periods of time in which we don't have good certainty on the phase of La Nina or El Nino, and that's where we get into the ENSO neutral phase, for example. When we do see uncertainty develop in the numerical models, that's when we fall back on short-term trends, but also climatology, or what we've seen in the recent term, to give us better guidance as we move forward. Finally, climatological outlooks. These are the products that are produced by the various climate models that we use on the short term all the way out to seasonally. And these give us an idea on the large scale setup of the atmosphere and the implications on the weather that we'll see out monthly and even out seasonally. So if we look at these climatological outlooks, these are probabilistic. They don't tell us how warm or cold we're going to get or how wet or dry we're going to get over a period of time. They give us the probability of being above average or below average. This is opposed to the forecast that we see on the news. Out 7 days, we're given a range of temperatures, the potential for X amount of snowfall, and what the winds are going to be. Those are forecasts. Outlooks are probabilistic, and they're based on various numerical forecast models. Also, those oceanic effects, the phase of El Nino or La Nina, the Madden-Julian oscillation, recent trends in climatology, how much snowpack is on the ground. If we have a broader snowpack, that usually yields colder temperatures, given that the albedo of snow reflects about 90% of incoming solar radiation, producing a net cooling effect at the surface. Now, the funny thing is when we talk about these climatological outlooks, we have the Farmer's Almanac and we have Punxsutawney Phil that more often than not get the news headlines. These are proprietary modeling. Punxsutawney Phil is how much cloud cover is currently over Punxsutawney, Pennsylvania. Our outlooks are based on science, so there is robust guidance when we look at these outlooks. Again, just to understand the probabilistic nature of these, precipitation on the left-hand column, temperature on the right-hand column. The darker the green, the higher the probability of being wetter than average. The darker the blue, the higher the probability of being colder than average. So these are how the probabilistic outlooks are developed. Gray in the middle, near normal behavior. On the bottom here, those white areas are what we call equal chances, or basically the climatological flip of the coin, above, below, or near average potential. We have, of course, that La Nina wintertime pattern that is really a good proxy for the outlooks that we've been seeing through wintertime, but also as we get into early summer or early spring. So remember this plot on the right to give you an idea of those outlooks that we'll see shortly. We have two short-term outlooks, 6 to 10 and 8 to 14 day. And all these outlooks will be the same, temperature on the left, precipitation on the right. The bluer the blues, again, the higher the probability of being colder than average. This 8 to 14 day outlook goes through the first week of February. And what it's telling us is we have a high certainty of colder than average temperatures across much of the United States, and then near normal behavior on the precipitation front. Again, February is one of the three driest months of the year, so it doesn't take a lot to be above average. It doesn't take a lot to be below average. If we look at the initial February outlooks, we have two varieties of the monthly outlooks. The initial outlook for February, which was issued on January 19th, and then the final outlook, which will be issued on January 31st. Again, showing a strong La Nina signature. Cold temperatures in the upper Midwest through the Pacific Northwest, but then two bullseyes of above average precipitation potential in the Ohio Valley and then through the Pacific Northwest. We're starting to see that precipitation probability shift slightly westward into Iowa. And this is a potential of a pattern shift in the larger scale atmosphere. We also often get asked, what are the snow potentials during La Nina or El Nino events? Given that this is the third year of La Nina, in all La Nina years since 1950, if we average those together, we typically get near normal snowpack, and that's where you see those white colors across the state of Iowa, but then above average snowpack across the upper Midwest. Well, an interesting thing fleshes out on slide 39 when we look at weak La Ninas versus strong La Ninas. In weak La Nina years, we are supposed to see above average snowpack, as we did in 2020. In strong La Nina years, we see below average snowpack. So if this wintertime La Nina that we're currently in comes to fruition, we should see above average snowpack. And we currently do see that across much of the state. Now, if we look at the potential on the left-hand side of a phase shift from La Nina to ENSO neutral, we see high probabilities. The higher the blue bar, the higher the potential for La Nina to hang around. We're seeing that into December, January, February, but then we start to see a downward movement of that La Nina phase. And in January, February, March, and February, March, April, we see a transition to a ENSO neutral phase of El Nino, La Nina. So it's right in between the cold and warm phase at 82%. Now, why this is important is if we look at, on the right-hand side, the March, April, May precipitation distribution for the state for each phase, El Nino, neutral, and La Nina. In the neutral phase, we see higher amounts of precipitation. When we look at higher amounts of precipitation in ENSO neutral years, this is a good signal to see given the drought conditions that we see across the state. Now, if we look at ENSO neutral spring analogs, or take all those years since 2000 in which we've seen a transition from La Nina to ENSO neutral, temperature on the left, precipitation on the right, we generally see a cooler signal, March, April, May, but we also see a wetter to near normal signal east to west across the state. This is great in terms of the potential for putting a dent in those precipitation deficits, but also more precipitation during the growing season to really feed the row crops that will get planted, hopefully on time this year. Finally, if we look at the February, March, April outlooks, we're starting to see some semblance of that ENSO neutral shift, where we do see the probabilistic precipitation field shift slightly west into Iowa. Now, again, we see those bullseyes in the Pacific Northwest and the Great Lakes and Ohio Valley on the precipitation side. But we are, as we start to ingest better data into the climate models, we will see that shift from La Nina to a more ENSO neutral flavored signal. Finally, the outlook summary. We do see that La Nina signal persisting through the winter season with widespread precipitation variability when we do look at those analog years. But overall, in a weak La Nina, we expect above average snowpack across the state. Finally, an 82% chance of a transition to that ENSO neutral phase through spring. Now, again, a slow transition when we do look at analog years from La Nina to ENSO neutral. But when we do see that ENSO neutral transition, we do see the chances of above average to near normal precipitation patterns through spring, east to west across the state. Here's my contact information. I'm on Twitter, Justin M. Glisan. There's the Climatology Bureau's website. Thank you for being a captive audience, and I look forward to interactions in the future.
Well, we want to thank Justin for that presentation. That was awesome information. I mean it seriously. Weather has such an impact on everything we do in agriculture. And while we can't predict the weather very well, there's no doubt that it has a huge impact. So I'm just going to talk for a few minutes here. I want to first highlight, talk about some of the really high yields we had this year for some of us, and talk through that a little bit and why that might have happened based on some information that Justin provided us. And then we're going to talk about Justin's future weather outlook and what we might need to be thinking about for the upcoming growing season. So let's talk about, despite the lack of precipitation generally across the state, there were some regions in the state that had well above yields, and unfortunately there were some regions of the state that had well below yields due to the persistent drought, as Justin mentioned, okay? So as I've talked to growers, there's been a lot of surprises, generally speaking, about the high corn yields and in some places even high soybean yields. And that's been a little bit surprising to some, and frankly a little bit surprising to me. But if you think about the general weather in the 2022 growing season, generally speaking across the state we were dry, but we had very timely precipitation events in parts of the state, particularly in the east central part of the state and the northeast part of the state, okay? And so those timely precipitation events gave us, just enough water just in time and enable us to reach those high yield potentials. The other thing we had, when we have generally a lack of water, we have generally a lack of clouds, which gives us more incoming solar radiation that the plant obviously uses to power photosynthesis, make sugars, and eventually make carbohydrates and proteins, which makes up yield, right? So we had generally higher incoming solar radiation also. So we had drier conditions, but lack of cloud cover and high incoming solar radiation. In addition, Justin and I were talking offline a little bit, and you've heard a lot of discussion about the smoke over the last few years with all the wildfires in Canada and out in California and the West in general. And initially you would think that that smoke would block the incoming solar radiation, and it does to some extent, but what it also does is it causes the solar radiation to be more diffuse. And what that does is it allows the light to penetrate deeper in the canopy and get some light on those leaves that normally would not be perceiving lots of light. And that's just good for maximizing the potential of these plants and increasing yield. So the smoke isn't always a direct negative like you would think it would be. In fact, it turns out that in a lot of cases it actually tends to be a good thing. So, I think between, the very timely rains and the higher than normal solar radiation across the state, that's why there were some surprises out in fields and we had such high yields in places. In other places, clearly the drought took its toll and we did not have record high yields. So now let's move on and just kind of very briefly wrap up what Justin said about the current weather and the future forecast. So the big takeaways that I took away from Justin's presentation are a couple things. Number one, we are generally across the state, we're still at a pretty decent soil moisture deficit. Okay, so that means that we should plan for a drier than normal conditions in the upcoming growing season, right? So if we do return to normal precipitation, that's great, and it looks like we might, that's great, but it's going to take some time for the soil moisture to catch up, because remember, as soon as things start greening up, we're going to start using that soil moisture again, all right? So it's not looking like we're going to have a wet growing season or wetter than normal soils in 2023. It's more looking like we're going to continue the drought and may start to recover from it, okay? So that's a good sign in general, right? So if we generally believe that we're still going to be lacking soil moisture, there's a couple things that I'd really think about, okay? I personally would do as little tillage as possible this spring, right? Sometimes we need to do tillage because we want to dry the soil out, right? But when the soil's already dry, that becomes less important. And what tillage will do is it'll open that soil up and it'll dry it out, which again can be a good thing in some years, but in a year where you're already lacking soil moisture, you don't want to do that. So not breaking that soil up is going to help hold that soil moisture in. The other thing that not doing a lot of tillage would do is it would leave some of that residue on the soil surface. And that residue does two things. It physically reduces, what it does is it reduces the amount of solar radiation that gets into the soil and warms that water up. And because that water stays cooler, you have lower evaporation of that water. So that keeping that residue on the soil surface keeps that soil cooler and reduces the evaporation of that soil water in those top surface layers. So the biggest thing I can tell you is if you don't think you need to do tillage this spring, try not to. If you do need to do tillage, keep it on the lighter side, don't go too deep. So lack of tillage or reducing the amount of tillage you do will help conserve that soil moisture. That's the biggest thing standing here today that I'd be thinking about. The other thing that I'd be thinking about is if you're a cover cropper, if you have cover crops growing out there right now, I would make sure that I terminate that cover crop just as early as possible. Cover crops can be good, but if you let them grow too long and get too big, they'll use up available soil moisture that your crop could have used. So if you have a cover crop out there right now, I would be pretty focused on trying to get it terminated as soon as possible. I know that also depends on the spring weather, but that is something I'd be thinking about. With that, those are kind of the key things that I'm kind of keying in on right now for the 2023 growing season. I wish you all the best of luck, and we'll have to wait for those future weather predictions, and maybe we can refine our recommendations from there. But as of now, those are the things I'd be keying in on. Also, don't forget tomorrow, we're going to have a panel of soil health experts. including myself. And remember, the core focus here with the soil health panel